Hi everyone, so let's get started. So today we have a talk by Jonathan. So he's going to talk about probability and in particular about random curves, and he's going to introduce you a little bit to Schramm-Loewner-Evolution's curves. Yeah.
Yes, so thank you, Nicholas, for the introduction. I hope you all can hear me. So as you said, this is a talk about probability, randomness, but more specifically, there is a randomness here that evolves in space somehow. So there's also geometry involved, and we will see that these curves that we look like are discrete in some sense. They are discrete objects, and we will try to refine them and see what happens. And then we will sort of take a look at this notion of a scaling limit, try to understand what that is, maybe also understand the name, what exactly is it that we're scaling here. But without getting too much into abstract sort of tangents here, we're gonna just jump right in, because that's one of the great things about this subject being very geometric. You can look. Then I get to.
I mean, now it's working.
Now it's working. Maybe I take this one just for. Like this. So what is going on in this picture here? So this is percolation, a very common model in probability that is quite well studied. So you see here this square, and on the inside the square we have a lot of hexagons, and they're sort of colored in many different ways. On the boundary I have prescribed the colors already. So you can see on the rightmost part it's generally white, and on the leftmost part it's all blue. But then inside of this square, I choose the colors independently of one another. So I flip a coin for each and every single one of these hexagons, and what I end up with is one large cluster of white to the right with smaller clusters of blue inside, and one large cluster of blue to the left with smaller clusters of white inside. And you can see here this red separating curve, which sort of separates these two large clusters, right? So the curve does something pretty crazy inside the square, but it respects these boundary arcs, right? So this is one way to look at a random curve. Obviously, since the coloring is random, so the curve must be. And now we can sort of scale this model in the sense that we use more hexagons while filling the same space. So instead of 20 by 20, we might scale it up to 120 by 120 or something like that. And you can see here, it's the exact same algorithm, but and the curve sort of does something that is fairly similar, but it's a lot more rough. So at each scale, we see a lot more roughness here, right? And one question you can ask yourself when you see something like this is what would happen if we continue to shrink the hexagons and obviously use more of them? Could we make sense of a notion of limit for this kind of process? And how would we describe this kind of process? Probably if we shrink the hexagons, we cannot really make sense of coloring infinitely small hexagons. So maybe there is another way that we need to think about how to describe and represent this limit if it exists. And we're not going to look too much into that specific model, but some simpler ones. But the same ideas apply, and many of the same ideas are also going to be used when we try to move into the continuum here. So the basic recipe for this talk is going to be have a look at a lattice, which is sort of the discrete base structure that we're going to use, and some random process or a sequence of processes that might be independent of this lattice. By this I mean, of course, a stochastic process, a sequence of random variables on a probability space. And the outcomes of these experiments are going to determine how the curve evolves. The first example, which is almost embarrassingly simple, is the random walk in 2D. So here I use the integer lattice, but I could, of course, also use something else, the integer lattice in the plane, that is. And I start at the origin. I have 4 possible directions, all with equal probability. And then I simply trace out the path that this random walker does. So I get something that looks like this black blob here. And but the interesting thing starts to happen when I stop the process. So say it exits this square, I stop the process, and then I have a path that I can work with. I can start to apply transformations to it. And one transformation that is particularly interesting is to erase all loops in chronological order. So I start at the origin, and then I check when is the last time that I visit the origin. And everything that is sort of part of that loop, I just throw it away. And then I move to some other vertex, right? And I repeat the process for this one. So this is chronological loop erasure. And this kind of curve is clearly self-avoiding or simple by design, and looks like this red one over here. But I could also, instead of letting a random walker do its thing and then applying this transformation, I could try to generate this red curve dynamically. So I start at the origin, and then equal probability of going to any of the neighbors. But then if I have arrived at a neighbor, say to the right or something, then I clearly cannot go back because the curve is self-avoiding, right? And you could probably write out like a difficult probability of transitioning to like a new tip point as this curve progresses through space. And one sort of interesting question to ask yourself is, what kind of information do I need to determine where my tip point of the curve is going to be next, right? So for the random walk, this the first example, I really don't need much information at all. I mean, it's really an equal probability of moving to any of the neighbors at each time step. But here it seems that I somehow have to respect that I might do loops, and that sort of influences the direction I might want to turn in. And you can think of it as, if I move in a direction that seems to indicate that I'm about to make a loop, I will want to steer away from that to sort of move back to a more straight path, which is also reflected in what you see here. It's something that is a lot more straight than you would expect from something that's just doing its thing, right? You have sort of obviously removed all the loops. And the trick question for you now is, in what sense is this latter process, the loop erased random walk, also a Markov chain? And so a Markov chain satisfies, it's a stochastic process which satisfies this Markov property that the transition probability in some way only depends on the previous, on the previous time step, right? And then it's also a question of what are these xn plus 1s? What it is actually that these experiments are, right? And to better appreciate how processes like these might actually be Markov chains on some state space, we're going to look at a model developed by Oded Schramm and Scott Sheffield in 2003. And for this, I would like to, use the board for a bit as well. So we have this sort of triangular lattice, and so lots of triangles, and one part of the boundary is colored red, like this, or the vertices of that part, and the other one is colored blue. And then I have points that are not, not vertices, but sort of lie on the edge between the boundary arcs. So I have V bar 0, and up here I have V n bar. And what I do now is I start here, I move into the center of the first triangle, and then I send out a random walker on the triangular lattice, starting here. It does something, and then maybe it hits this part of the boundary, and then I'm going to turn away from that part in here, so into this new triangle. And what do I do? Well, I start a random walker from here. Oh, sorry, very important. So I turn away, but I also update the boundary. So I add this point to the red boundary. And now I am in a similar setup, right? So I have some sort of boundary arc here, a boundary arc here, and the setup is exactly the same. I can repeat this process for this new vertex here. It turns out that it sort of, in my picture at least, is in the boundary, so it's blue. So then I turn away from that part of the boundary. I come up here, and I don't have to do anything because it's already in this part of the boundary. I start a random walk from here. Let's say it hits the boundary, the blue part of the boundary. I turn away from it. So as you can see here, there is a process that somehow avoids the boundary by being scared of coming too close. And the random walk that I send out sort of measures how close I am, right? So I'm a lot more likely to hit a boundary, like the wrong part of the boundary, or the blue part, say, if I'm very close to it. And now I could, yeah. And what this gives rise to is a picture like the one you see to the right here, where you have something that also a bit similar to the loop erased walk. It sort of steers clear of this risk of doing a loop in some sense. And it actually turns out that this way you can produce a curve which starts at the point V0 bar and ends at V bar end. These are the bottommost and the topmost points that sort of separate these arcs. Exactly, so we send out this random walk and we record the color, and we turn left or right depending on the color. But we also update the boundaries, so we color the vertices that we sent out to walk from according to the exit color. And this gives rise to sequences of new boundary arcs, right? Which also implies, given that we have information about the original domain d hat, it sort of implies a new domain where we have cut out the curve. And remember I told you that the setup is really exactly the same in each time step. We have some sort of domain where this process sends out a random walk to check where it's going to turn. And this has as a consequence that we can actually start to think about these processes as Markov chains, but on a slightly different state space. We have this freedom to change the state space and consider instead tuples and triples. So a tuple of a mark domain, they call it, in the case of loop erased random walk. So here AN is the original domain where we cut out the path that has already been taken by the loop erased random walk. And in the case of the Harmonic Explorer, it's a mark domain where we have something very similar, but we also append the ending point. And that then implies exactly all the information we need, how the boundaries are set up. And you can actually write down what the transition probabilities are in that case. It looks kind of scary at first, but it's actually completely in terms of the geometry of the domain we created in the previous step, right? And so that's the first line for the loop-erased random walk, and the second line is the probability that a random walk hits some part of the boundary. I gather that many of you in the audience are mathematicians. Like I recognize many of your faces. So probably some of you have heard about harmonic functions, discrete harmonic functions even. And we're going to see later that this h of n is such a discrete harmonic function and related a bit to that. But again, we need to consider loops and discrete harmonic measure. That's a whole talk in and of itself, but a very, very interesting direction to go in. Now on to the scaling limit idea here. So you have likely all heard about the central limit theorem, and this idea that if you have a lot of small effects that you somehow aggregate and scale appropriately, you're going to converge to a normal distribution. And something very similar is going on here. So in the first picture, you see a random walk, which I have linearly interpolated between time steps. And in the second picture, you see a simulation, a discrete simulation, but still of Brownian motion, or what is supposed to be a Brownian motion. And if you look at the time dimension, I think it's 100 in the first picture and 10 in the second one. So the Brownian motion does a lot more crazy stuff in a shorter amount of time. And if you look at the first process and you start to scale it like this, you scale the time dimension, you speed up time so you get more of these increments in a shorter amount of time. But you also scale space by a factor that is, 1/2, like what you would have for the time dimension. Very similar to the central limit theorem, you actually get that this process here converges in distribution to Brownian motion. And what conditions do we put on the increments here? Very little, actually. So up to rescaling and stuff like that, we need some certain mean zero, we can say, but also like unit variance. But other than that, we don't really make any claims as to what the increments of the random walk should be. And the significance of that is that a large class of slightly different discrete models all converge to the same continuous model. So the continuous model is more natural, right? And if we extend this to the two-dimensional case, we're going to see that a 2D random walk converges to a 2D Brownian motion, like a complex Brownian motion. And then you can actually start to apply interesting transformations. So it turns out that Brownian motion is conformally invariant, which we will formulate a bit later what that means. But the main takeaway here is that we gain symmetries. So something that was first only rotationally invariant, as the random walk is now also conformally invariant. So a conformal transformation, we have that it is locally a bit like scaling and rotation. And so together, like Brownian motion has this scaling property, so it's scale invariant, but also this rotational invariance of the random walk sort of translates together with the scale invariance to a conformal invariance of the Brownian motion. Now, if we want to take limits of these more complex models, there are some different approaches that we could take. We could either say that maybe I'm interested in the Harmonic Explorer and I want to see that it is conformally invariant. whatever that means, then I could try to see that this property is either preserved or gained in the limit somehow. Like that's one idea. Then I wouldn't really need to know what it converges to, but I could say that, you know, it's rotational invariant, and this rotational invariance sort of translates to, like, in the limit, these probabilities seem to behave in the way that I would expect given conformal invariance. But another, maybe more fruitful way of working these properties out is to actually work with the representation of the limit. So instead of saying, you know, I don't know what the limit process is going to be, I'm going to say, you know, this is my target limiting process. It has certain properties. And now all I need to do is show that my process actually converges to that one. And as we saw, there is a lot of geometric information going into the formulation as Markov chains, right? So to actually take these limits, we're going to have to zoom out a bit and develop some theory. So this is Loewner's theory. It's not stochastic at all to begin with. And you know, the central object, we are in the upper half plane. The central object here is a hull K, which is a compact set where the complement is simply connected. So it might look something like the blob, the black blob up there, or it might be a curve. And we can use Riemann mapping theorem to get that there is one, and it's unique, a conformal isomorphism from this complement to the upper half plane, which looks like the identity at infinity. So what this means is really we can think of it as this map sort of pushing this blob or this curve, whatever it is, down into the boundary of the upper half plane. And it does so in a way so that the angles between curves, the grid lines of the complement here, are still preserved. If we look at this map, it has an expansion like this, and this quantity A sub big K, which we call half plane capacity, and somehow it is a measure of the size of this blob. So if the blob is rather large, AK is also going to tend to be larger. It's not a perfect measure of the size, but it sort of gives you some handle on the size. The idea now is going to be to look at a sequence of growing hulls, right? So you have hulls that are sort of that describe the evolution of a curve. So there's this hull K that's growing, and the associated mapping out functions G sub KT, and you know, it turns out that we can reparameterize the time by half plane capacity. You should think of this as normalizing for the speed of the growth of this blob, right? So you normalize for that. And then it turns out that for a fixed C in the upper half plane, the image of that C under GT satisfies this differential equation. And we have this driving process term W. And the interesting thing here is that you can there is a correspondence here, modulo a couple of technical details. There's a correspondence between the curve and this driving process. And maybe I could just show you quickly on the board what this might look like. And again, a bit similar to what we discussed about the loop erased random walk and also the Harmonic Explorer, there's this notion of you're steering away from something. And so this driving term W of t might be doing something like this. And in the upper half plane, that is going to translate to something that's it's steering a bit in this direction, and then it's going like that, and and you could also imagine that if you start doing some crazy stuff. It might translate to sort of very erratic steering behavior as this curve grows. And a natural question for anyone interested in this kind of analysis and translating back and forth is how rough can you make this driving term W, right? So now I would go back to the presentation slides and talk a bit about what Schramm's main idea was. So his idea, updating Loewner's theory to Schramm-Loewner theory, is to take W to be stochastic in some way. And in particular, he's gonna want to use this scaled Brownian motion. So this driving behavior is going to be extremely erratic, and you're going to get probably a curve which is very, very rough. And it turns out that different values of kappa give very different behaviors. I think the picture you're seeing here is SLE2. So it's a lot more of a straight curve, right? But if you took, I think, around 4, it's already going to be a lot more erratic, going more and more to the side. And I think there is some value where it's also space filling, right? So why is this SLE family of curves, why is it so special? The setup is really the following. In statistical physics, we are interested in considering continuous models where we have a family of measures which are indexed by a domain D and 2 points, and a measure that can be used to sort of measure the likelihood of seeing a given set of curves which start at A and end at B and are otherwise contained in D. And if we consider the push forward of one of these measures for a conformal isomorphism, this equation tells me that it's really enough for me to know how these curves behave in one domain, and then I can tell you about all domains that are conformally equivalent to it, right? So instead of having to know all possible f of d and stuff like that and how the family of measure behaves there, I can simply look at one domain D, say the unit disk or something, 2 points in it, and I can translate whatever question I have in some other conformally equivalent domain. I can translate that back to my original domain and answer all questions in that domain. And the second thing that we will insist on is the domain Markov property. So this states that if I know the curve up to time t in my domain D, and I'm interested in the probability that the rest of my curve lies in some set B, this probability is the same as measuring with respect to a new measure where I take away the part of the curve that has already been taken, already been traversed, and I measure it from the tip point gamma t. So again, what's the idea here? Well, the idea is that somehow this conditional probability is captured completely by geometric information. Like it's captured completely by another measure in this family of measures. It's captured completely by another measure indexed, by some domain, some point A, some point B. And it turns out, and this is Schramm's principle, that SLE curves are the only random curves in the plane satisfying conformal invariance and this domain Markov property. So now with this information, we know that if we expect the Harmonic Explorer, for example, to be conformally invariant in the limit, and if we expect to somehow capture this, we said before that it is a Markov chain on this very geometric state space. If we wish to sort of have this be transferred into the limit, it actually has to be some SLE curve. That's the only option we have. But the question is, what value of kappa should we aim for? SLE kappa, you could have 1, 2, anything in between. You could have, I guess, 8, and beyond that, you don't really know exactly yet what the qualitative properties are of SLE, but why couldn't you just scale your Brownian motion by really any positive kappa, right, or a square root of kappa? And to sort of get a good guess at what the value of kappa has to be, we're going to have a look at some qualitative similarities between the Harmonic Explorer and SLE4, actually. And remember I talked before about the exit probability. So the exit probability, if you start at the vertex and you start a random walk from there, the probability that you hit the red part of the boundary, right? Now you could also ask this question not only for the vertex that is sort of very close to the tip point of the curve, you could also ask it for any vertex inside the grid domain, right? And you could do something very similar here for the SLE curve, but replace a random walk with a Brownian motion. So you start a Brownian motion, a 2D Brownian motion, in some part of the upper half plane, and you check, what is the probability that it hits this SLE4 curve, either like on the right-hand side of the SLE4 curve, or that it exits through the segment 0 to infinity. Okay. So these are sort of analogous in the sense that you consider the red part of the boundary plus sort of the right part of the Harmonic Explorer curve with a random walk, or you consider in the SLE case the right part of the SLE curve or the segment 0 infinity. And it turns out that in both of these cases, I'm just going to state it here for the Harmonic Explorer, it turns out that these probabilities that obviously have to change as the domain changes, right? That these probabilities for a fixed vertex, this is a martingale. Okay. So I tend to expect it not to change in the next time step. And this is quite easy to see for the the vertex that is really close to the tip point of your curve. It's like slightly more difficult to see that it holds for all vertices, but it holds for all vertices. And it also turns out that both of these exit probabilities are discrete harmonic versus harmonic. And this really unlocks the proof idea. It's something called a martingale observable. It's something that's used in many of these SLE proofs. And it's really helpful that for each vertex we have a martingale, right? And it's gonna allow us to say something about the driving process of the Harmonic Explorer curve. To do that, we first have to map the Harmonic Explorer to the upper half plane and compare the driving term to that of SLE4 there. But it turns out that if you make this grid domain larger and map it to the upper half plane, we actually have this convergence here. And depending on the audience, I thought that I would go into slightly different directions here. But I think that since many of you seem to follow very nicely, I could maybe discuss a bit, what exactly is going on in this proof. So, as I told you, there is this notion of a discrete harmonic function. It satisfies the mean value property, which is also satisfied by normal harmonic functions. But they're usually sort of defined by the Laplace operator, but they satisfy this as well. And the probability that a random walk started at a vertex V hits the positive part of the boundary at some time step turns out to, it depends on the domain, but it also turns out that this function for a fixed n is a discrete harmonic function. And the way to think about this is, you start at some vertex, and then the probability that you're going to exit at the positive part of the boundary is, you move to one of the neighbors, and from there, you just look at the probability that you're going to exit from there, right? So it satisfies this mean value property. A martingale, I probably don't need to define this for the given audience, but it captured this idea that my best guess for the next random variable in the sequence is sort of the previous. And this filtration here is encoding the sequential gain of information, which we're going to take to be this very geometric information that we have from what the curve has traced out. And as I said, this Hn of V is a martingale for each vertex V. This martingale observable. And as I told you before, something very analogous holds for SLE4. We can consider this exit probability through this segment or on the right side of the curve. And so the Harmonic Explorer lives in some domain. We consider making this domain larger and larger, then map it to the upper half plane. And then this mapped curve, this mapped Harmonic Explorer curve is going to have a driving term according to Loewner's theory. And so there is this qualitative similarity between the exit probabilities that we're going to try to exploit. We're going to change it up a bit. We're going to use the exit probability for the Harmonic Explorer mapped to the upper half plane, but the exit probability of a Brownian motion. And this turns out to be a very good approximation for the exit probability for the Harmonic Explorer random walk, right? This is not trivial at all. It's one of the more difficult steps of the proof, showing that this is a good approximation and that it's also, good for a long enough time frame and for enough vertices, for more than one vertex specifically. And but the general idea here is that the discrete quantity can somehow be approximated by a continuous one. So this exit probability for a Brownian motion turns out to be a nicely behaved harmonic function. And it can also be written in terms of this driving process. And for continuous functions, that are also differentiable, we can use Taylor expansion. And this leads to an equation of this form. This sort of pops out from the Taylor expansion. So again, we use a qualitative correspondence between these exit probabilities. We make a good enough approximation, and then we approximate the approximating quantity by this Taylor expansion. Some really nice coefficients pop out. And this is just shorthand for conditional probabilities of certain increments. And if we do this for two vertices, we get a linear system. And we can get this result here. And I I have not written it out in full detail, but basically what it says is, this is exactly the local behavior that you expect from something that is a Brownian motion scaled by a factor 2. And this holds for a very short time frame, but you can actually patch this together for a much longer interval, so 0t for any finite t. And then you get the result that the driving term actually has this convergence. The next step would be to show that not only the driving term converges, but also the curves themselves, that the curve itself becomes very close to an SLE curve. That's not necessarily implied. But this kind of martingale observable proof where we have some discrete harmonic quantity that it can somehow be used to show a convergence is something that generalizes well beyond Harmonic Explorer. It's also used in the case of loop erase random walk to SLE2. And the idea is for each vertex V, we get a martingale. We have freedom to choose which vertex we want to use in this setup. And in the end, we need 2 for each such local statement, and many such local statements and approximations to patch together on the whole interval. And if you're interested in this kind of proof, I recommend you to check out these 2 papers, which were written in 2003, I think. So the first one is by Oded Schramm and Scott Sheffield. It's on the Harmonic Explorer. And the second one deals with a lot of models, but of most interest is probably the loop erase random walk. And it's actually showed that it converges to SLE2. And Wendelin Werner, which he was here at TDH before, this was like a big part of his Fields Medal, I think. So it's a really interesting paper. And if there are any questions, I think we're quite short on time, but yeah, that's all for this talk. So thank you so much for listening. Yep.
Maybe I have one question on that. Can you go back to Schramm principle like that? Is fine.
Yes.
Maybe can you re-explain the conformal invariance? I'm not sure I really understood what you meant.
Yes. So one way to think about it is you have this family of measures that so for each such triple at domain D and 2 points where you sort of fix starting and end point, you have a measure that measures how likely is it that a set of curves, with a property that it starts at A and B, how likely is that this kind of curve is going to occur, right? So it might not be a single curve because it has probability 0, but it's like a set of curves that you can measure. And the idea here with conformal invariance is that if I have some domain, some simple domain, maybe the unit disk in the complex plane, and I know how the measure behaves in this simple geometry, and I'm interested in understanding how the measure would behave in a different geometry. That question can if I know what kind of map conformal isomorphism F moves me to this different geometry, I can completely answer this question just knowing what I know about the unit disk, for example. So I can simply take whatever set of stuff is happening in this different geometric domain, I just translate that set of curves back into the unit disk, and I measure these curves in there, and that's what this push forward is about. and that's what this doesn't hold for all f, by the way. It's also it only hold. We only insist on it holding for conformal isomorphism. So that's the idea, and the idea here is that SLEs are the only such curves in the plane that sort of satisfy that and this domain Markov property. Yeah. Yeah.
Maybe detail what you mean by exit from the segment 0 infinity.
So yeah, so you mean the Brownian motion? Yeah. So let's say I start at the point. What point can we take? So a point in the upper half plane, which is not already touched by the SLE curve. And then I start this Brownian motion, and it does something. And at some point, you know, it's gonna exit through the upper half plane in some way. Either that, or it's gonna touch the SLE curve, you know, either on the left side or the right side. You know, and if it touches on the right side or on this segment, I consider that to have hit the positive part of my adapted boundary, right? So, and the idea is why do I care about the right part of the SLE curve? It's exactly to sort of mimic this. For the Harmonic Explorer, you can see that the boundary arcs follow my Harmonic Explorer curve on its way. So I color the vertices close to the Harmonic Explorer curve. So it's just to capture that that qualitative similarity that I also care about the right side of the SLE curve. And it's not obvious, but it turns out that this is behaves very similarly, and that it's actually, you know, a good approximation, one or the other. Yeah. Yeah, then I think that that's it. So thank you so much for listening, and let's enjoy the apéro. Yeah.